Hello, this will be the introduction to the ball screw simulation at the Meshparts company. The ball screw simulation cannot be replaced by measurements or analytical calculations. There are some good reasons why this is like this. For example, when you are designing a ball screw, you are interested in the contact pressures of each single ball, and this is a very difficult thing to measure with experiments. So you want to be able to look inside of the ball screw, and we are pretty limited when doing experimental measurements. So there is a demand for high precision simulation of the ball screw behavior, a simulation that is able to predict the real life behavior of the ball screw. The finite element analysis, FEA, is the best way to address the different requirements of the ball screw simulation. Modeling ball screws with traditional software can be a very demanding and difficult task. For this reason, the Meshpart solution relies on a predefined parametric library of ready-to-use finite element models. And since we have access to a library of finite element models, the modeling of ball screws is reduced to filling up a table of parameters, which I want to demonstrate in the following. When we simulate ball screws, we start with a so-called ball screw wizard. The ball screw wizard is actually a Microsoft Excel table that simplifies the input of the user through interactive graphical user interface. You can see here that we see the sketch of a single nut ball screw, and in the second sheet you can see the sketch of a double nut ball screw. In the single nut you can see that you have different dimensions which actually describe the full ball screw, and each dimension contains a field where you can enter a dimension. For example, if we want to change the pitch of the ball screw, we can go into this entry here and input a number. For example, 7 millimeters. Look at this cell, the D2 cell in the table. You can see that I already have the entered value in this cell. For example, now if I change it to 8 millimeters, the cell will update. So actually, I have two ways. I can input the values here in this row of values, or I can input the values here in the table. The same thing is valid for the double nut. We can input, we must input a little more values here for the double nut, since we have two single nuts that are pre-tensioned. But basically, when I'm done with filling up the table, what I have is a row of ball screw parameters, which we call a ball screw configuration. And the name of the ball screw configuration is written in the first column of the table. In the next step, there is a second table that contains all available ball screw versions or configurations. You can see here in the table we have a total of 6 ball screw configurations, and each configuration has a different name. I can easily copy the one available configuration, go back into the ball screw wizard and input the selected configuration and copy paste. Then there is a button here, get from cells, that will take the values from the configurations, from the available configuration, and put it into the fields of the sketch. Then I can, for example, adapt an available configuration by changing values here directly. Again, for example, if I change the pitch, this value will be transferred to the row of the configuration. And then I can select the configuration, go back in the table of all configurations and copy paste the new configuration into the table. Of course, it's a good idea to assign a new name for this configuration. Okay, so when I'm done with defining all or just one configuration of my ball screw, I must go into the Meshparts software and create a new ball screw from this configuration defined in Excel. You may ask now, how is this possible? How can Meshparts create a ball screw finite element model from an Excel table? Well, we have here a predefined assembly of a ball screw which consists of basically three different components. We have here a ball screw nut, a ball screw spindle, and each single ball. You can also notice that the mesh is already optimized for the task of computing contact pressures resulting from an external load on the ball screw. Also here you can see those refined areas only at the contact points, since I don't need a very fine mesh in other areas. This model is completely automatically generated based on the available Excel configurations. Now, I want to change this configuration because I have a new one defined in my Excel table. Let's see. I select the main assembly, and here in the field of assembly equations, I must enter the name of a new configuration. Let's see. We have, for example, here a configuration for single nut, V3 and V4. Let's try this. When I have changed the name of the configuration, I just click Save and Apply. And you can see how the model is updated accordingly. Now, if I take a look here, I can see that, well, the number of balls obviously changed because now I have different geometric parameters and also the regions for the different ball circulations are different. So you can see this whole thing works very, very fast. We can also try to generate the V4 configuration. The same thing, we change the name here of the variant and then click on Save and Apply. Now this is a much shorter ball screw. You can see that we have a much less balls. And since we are talking about balls, there are different ways we can model the balls, and this is a very important aspect because this greatly influences the efficiency of the model. Now here you can see that we have flexible balls, and each ball is meshed with tetrahedrons. The problem with this kind of modeling is that normally this kind of model would require a very fast computer to solve. So basically this model would never work on a normal workstation. And this brings me to the next point of my presentation. The type of balls used in ball screw simulation. The first one you already saw is the flexible ball model. The flexible ball model is able to numerically compute contact forces, and also it allows it to numerically compute contact pressures. But the problem is that this model is extremely inefficient. And like I said, it's impossible to solve it on a typical workstation. The next model that we have developed is the ribbon model. The ribbon model allows you to numerically compute contact forces and contact pressures and is very efficient. You can get results from such a model in up to 12 hours, which is very fast actually for a Borsco simulation. Well, if the ribbon model is too slow for you, we have a third model, the ROX model, which allows you to numerically compute contact forces, but the contact pressures are analytically computed. The reason for that is that the ball screw model, as you can see here, it consists of simply two nonlinear springs, and the forces of those nonlinear springs are transferred to the ball screw spindle and not through a bigger surface than in reality, so it's not possible to compute numerically the contact pressures. Nevertheless, this kind of modeling is highly efficient as it allows to compute results in about 10 minutes. So we have the choice what kind of model to use, the ribbon model or the ROX model. So for example, if I decide to use the ROX model instead of the very inefficient flexible models, I can go into the library of Meshparts and choose, for example, a new model here. Let's select it and drag it over the old version of the ball, which was flexible. And what you can see now is that the balls are updated to the ROX model, to the ribbon model. There is also another predefined assembly for the ball screw that contains the ROX models. You can see it here. Like I said, the ROX models consist of nonlinear springs, so there is no 3D geometry describing the balls. We have only those nonlinear springs here, which are still very near from the accuracy to the 3D balls, and have the advantage that the simulation time is extremely short. Let's see what happens if we change the configuration here in the ROX assembly. It goes the same way. We can change the configuration name and click Save and Apply. And here you go. You have a completely new ball screw model in a matter of seconds. Now that I'm done with modeling, I can apply and define loads and boundary conditions. I have done this here. You can see that there is the flange surface selected, and this surface is fixed in all degrees of freedom. Then there is a load applied to the end surface of the spindle. This is the force here of 10,000 newtons. And also there is a constraining of the rotational degrees of freedom, because we don't want that the spindle will start spinning in a statical simulation. So when I'm done with defining the right ball screw configuration and updating the finite element assembly, I'm ready to go, and I can solve the model. So for this, I have to select the assembly in the model tree, and on the right side of the graphical user interface, I have a button that will start the simulation process, And there are some options here. You can see, for example, that we have the choice between an ANSYS format or Abacus format. So this is a very important thing to know. Meshparts provides a, a meaning of creating very efficiently different models, not only for ball screw but also for other mechanical components. But we don't provide a solver. So the solver, we rely, when it comes to solve the finite element models, we rely on state-of-the-art solvers like ANSYS or Abacus. Also, we can specify the type of the solution, which in our case is a statical solution. So this would be actually everything. You just have to click on this button, and then an ANSYS solution job will start, and will finish solving this model in about 10 minutes. I have already done this, so there is no need to repeat the solution job in this case. Um, we can we can see how the results are by opening the folder, the directory where the model is available, and in the directory of the model we can find two DAT files which contain the results of the ball screw. And when I talk about results of the ball screw, I'm speaking about contact forces and contact pressures, and also some other results like the dimension of each single contact ellipse. Meshparts automatically outputs those results for each single ball in those DAT files. You can see here how the DAT file looks like. It's a column-based format. You have different columns for different results, and each single row stands for a ball. And we have two DAT files because the one is for the inner race and the other one is for the outer race of the ball. So basically, the one is for the ball screw spindle and the other one is for the ball screw nut. Now, of course, just looking at this table won't help a lot to understand how the ball screw behaves. The best thing to do now is to select the content of the file and then go into Excel and post-process the results there. You can see I already did that for the spindle. And what I can do is to plot some diagrams. For example, here the contact force. We'll plot the contact forces for each single ball. You can see here a step in a jump in the force. This comes from the two ball races. In the next diagram, you can see the contact pressures. See that the diagram is created by selecting corresponding columns in the table. This diagram shows the size, the length of the contact ellipse, and this one shows the change in contact angle. This ball screw had originally in unloaded state a contact angle of 45 degrees, and you can see how with increasing load the contact angle reaches up to yeah, 84, almost 48 degrees in a loaded state. I can demonstrate how to create the same table for the nut. I select the outer race DAT file, copy the contents, then select this cell and import the data. Here we need a ball numbering, and now I'm ready to go. I can select the first two columns and then insert a new diagram like this. And then, for example, if I want to show the contact pressures, I have to scroll further to the right, and I can then do the same thing, insert the contact pressure. Now you can see how simple this can be done in order to evaluate each single ball and the results of each single ball. Next step, we can also visualize the results. Since the whole simulation was performed by ANSYS, there is also a ANSYS DB file available that you can open. And let's see how the model looks like in ANSYS. This is it. I can go into the general post processor and select plot results, contour plot, and for example the total deformation with a user specified scale factor of, let's say, 100. Let's see how this looks like. I can increase the scaling in order to see more, and also I can create a section view. I have already written some APDL commands in order to do that. Yeah, you can see now how this is a better way in order to analyze the way the spindle is deforming. For example, you can see that there is a tilt. This comes from unsymmetric repartition of the balls. Although the force is acting perfectly axial, there is an asymmetry in the stiffness, so the ball screw will have a tilt. And this is also the reason why you can see here that the forces are not constant, and there is a sinus shaped curve describing the forces. Basically, this corresponds to one cycle of the balls. We can also animate, of course, those results. You can see how the whole thing deforms. Also noticed that you don't see the balls in this animation and this model. This is mainly because we have used the more efficient ROX models instead of the Rebem models. So actually that was it. You can see we have put a lot of effort in automating the whole process of modeling ball screws, and I think we have achieved a big achievement in this area. I hope you liked it, and if you want to know more, you can go and visit our website www.meshparts.de for more information. Also, for if you have any questions, I would be happy to answer your questions. Thank you and bye.